Yeah.
All right, thanks for coming. So today we have a Kyle from Georgia Tech. We'll talk about something on Paley graphs, maybe ranging. Please.
Okay. Thank you for the introduction, and thank you for inviting me to speak. It's great. It's my great pleasure to be here. This is a joint work with many people. So including Shoyoung Kim and Sammy in the audience, and also Shamil Asghari and Jules Flower, Sergey Garinov, Greg Martin, and Leonid Sarajinov. I want to first introduce Kelly graphs and Paley graph in case you haven't heard of that, but I don't think that's the case because Sammy maybe gave 1 or 2 talks on this topic. In this talk, we will work on finite field. So FQ is the finite field with Q element. And the most important thing is that if we consider FQ star, which is all the non-zero element in FQ, it forms a cyclic group. So that's one very important fact about finite field that will be used in this talk. For the Kelly graph, basically, we first consider a connection set S, and then we are saying that 2 vertices are adjacent if there are differences in the connection set S. So to make this graph undirectly, we need to make sure that S is symmetric, namely S is equal to minus S. So for Paley graph, we are just taking the connection set S to be the set of squares. To make sure that the connection set is symmetric, we need to assume that -1 is the square in the field, so that means we need to assume Q is 1 multiple. Okay. So for example, let's just consider the case Q equal to 5. In this case, let's just try to consider the 5 elements 0, 1, 2, 3, 4. Right. So we consider the set of squares modulo 5. So you can check that squares are just given by 1 and 4. Right. And this is the same as 1 minus 1. So the Paley graph on 5 vertices is just C5. Right, because the connection set is just 1 and minus 1. And here is a example of Paley graph on 13 vertices. So the underlying field is F13, finite field with 13 elements. And you can see that this is a pretty nice graph. So we'll also talk about cyclotomic graphs. So this is just kind of like the generalization of Paley graphs. So for Paley graphs, the important thing is that, the important thing is that here, connection set is a set of square, which is actually a subgroup of index 2. So we can try to just replace this subgroup of index 2 by an arbitrary subgroup. For example, if we let H to be a subgroup, then the connection set with being H means the graph is called a generalized Paley graph. So if the subgroup has index D, it's called a D-Paley graph. So the special case of Paley graph is just we take index 2 subgroup, subgroup, which means the set of squares. And for cyclotomic graphs, the idea is that sometimes we want to consider the connection set not just being a subgroup, we want it to be the union of some coset of subgroup. For example, if H is a subgroup of index 5, we can take 2 cosets of this subgroup, and then we put them together to get the connection set S, and then we get a cyclotomic graph. So I guess the initial motivation of studying cyclotomic graph is to construct new families of strongly regular graphs, but the cyclotomic graphs are also of independent interest. Okay, so the focus of this talk is that we study some graphs which are close to cyclotomic graphs, but they are maybe not exactly cyclotomic graphs. So before talking about that, I want to make some connection between clique number of such graphs and some problems in arithmetic complex. So for clique in this kind of Paley graph, it just means that we want pairwise difference to lie in the connection set S, because that's the definition of a Paley graph. So two vertices are adjacent if there are differences inside the connection set S. So now if we have a clique, that means that all the pairwise differences are in the set S. So that means C minus C, which just collect all the pairwise differences is inside the set S yielding 0, because we also have 0 in this different sets C minus C. So this means that if we try to understand the clique number of X, this is similar to studying the additive structure of S, because we are trying to say that S contains some C minus C. So this is related to the additive structure of S. So the question is most interesting if S has some multiplicity structure. So we are saying that S has some multiplicity structure, but it also has some non-trivial additive structure. So this is related to many problems in arithmetic complex. So I mentioned the sum product conjecture in the next slide. But first I want to make some assumption on which kind of S we will talk about in this talk. So we will focus on precisely those S which has strong multiplicity property. And by saying S has strong multiplicity property, I mean that S has small doubling. So that means that if we consider the product set S times S divided by S, this is a small set. So in particular, if S is a multiplicity subgroup, then S times S is just S itself, because subgroup is closed under multiplication. So in that case, it has perfect multiplicity structure, because the doubling constant is just 1. And why do we care about doubling constant? The reason is that doubling constant essentially measures the multiplicity structure of the set. So one particular case is that we have the so-called famous Kuhn-Ruja inequality, which says that once we have a control on the doubling constant, we can essentially control all kinds of product set. So for example, you can consider this set, which would appear in the later slides. So this is just S times S times S inverse, S inverse, S inverse. So essentially, it's just a kind of an iterated product set and also a ratio set. So S inverse just means all the X inverse where X is in S. So if we have some control on the doubling constant, we can bound this by k to the power 6 times S. So doubling constant provides an effective way to measure the multiplicity structure of a set S. Okay, so next I want to mention the sum product conjecture. So sum product conjecture is still widely open, and it has many generalizations and variants. But for our purpose, let's just consider some special case. Given a nice ring R, so in our case the ring R is just a finite field F cube, and we have some subset of this finite field F cube, and suppose this set is not too small. Then the sum product phenomenon says that A cannot be simultaneously very additively and very multiplicatively structured. So by that I mean that either the sum set A plus A or the product set A times A must be much larger compared to the size of A. With one obvious exception, namely A is close to be a subring of R. Because if A is close to be a subring of R, then A plus A and A times A is just A itself. Subring is closed under addition and multiplication. So the sum product phenomenon essentially says that if we are not in the subring situation, then one of the sum set or the product set has to expand. Okay, so why is it related to our problem? So we are saying that we are working on a Paley graph where the connection set S has nice multiplicative property. Okay, so suppose now we want to consider the clique number. So that means we want to find the maximum size of the set C, such as C minus C is contained as union 0. Right? So suppose C is kind of large, then this means that S has some nice additive property, because C minus C itself has nice additive property because it's a different step. But on the other hand, we also know S has multiplicative property by our assumption. So now S has both nice multiplicative property and also additive property. So the sum product conjecture says that it cannot be large, because if it's large, it's wild and conjecture. Unless we are in the situation that our clique has some algebraic structure, namely it's a subgroup. So in our case, because we are working in a finite field, so we know that we have both addition and multiplication. So in this case, the subring could mean a subfield, but sometimes it could also mean subspace. So that means that typically we would expect the clique number to be very small, unless we know that we have some obvious clique which comes from either subfield or subspace. Okay, so that's kind of the motivating idea for this kind of clique number question. So any questions so far? Okay, so next I would like to just show the so-called trivial upper bound of the clique number for a family of graphs where S has nice multiplicative property, in the sense that if we consider the ratio set S over S is not given by the addition. So for example, if S is a subgroup, then of course S over S is S itself, so it won't be addition. So in general, if S has nice multiplicative property and S is not too large, then we can maybe show that S over S is not given by this. So this applies to a very large family of graphs. So in this setting, we are saying that the clique number is at most square root Q.
So S over S, it means you multiply X with some inverse of
Yeah, let me just write down the definition. So S over S means we take all the possible ratios where X and Y are in S. Yeah. Yeah, sorry, I should define some set for the set in the first slide. Okay, so let's try to see how to prove this. So the idea is that we can try to pick something outside of the ratio set, say G. And then we can consider this set W, which is Vi plus G Vj, where I and J runs over 1 up to n. Then the claim is that all of these kind of sums are different. So we know that W would have size n squared, and W is of course a subset of the finite field FQ, so it has size n minus Q. So this will show A is n minus square root Q. So our task is to just show that they cannot be equal. So let's try to prove by contradiction. So suppose this can be actually equal, where ij and I prime j prime are not equal. Then after doing some rearrangement, you can see that we can write G as a ratio set. G as a ratio. So if you just move Vi prime here and G Vj here, you can see that G is equal to Vi minus Vi prime over Vj prime over minus Vj. And because our set is a clique, you know that this difference lies in the connection set S, and also this difference also lies in the connection set S. So G lies in the ratio set S over S. So that contradicts our choice of G. And so this proves that the number is at most square root Q. So this is known as the trivial upper bound in the case of Paley graphs. Okay. So next I want to discuss when is this trivial upper bound tight. Suppose that our Q is a square, So say Q is R squared, then we know it has some subfield, right? So Fr is a subfield of that Q. And also suppose that S contains everything in Fr except 0. Then we know that Fr actually forms a clique in X. Because if you use Fr minus Fr, we just get back Fr. So if S contains Fr star as a subset, then Fr itself forms the clique, right? So this shows that in this case, the Q alpha bound is tight. Okay. And let's look at the special case of Paley graph. So just recall that Paley graph is that our connection set is the set of squares. So I want to show that if Q is a square, then actually in this case, the Q alpha bound holds because the subfield of size square root Q actually forms a clique. So to do that, we need to use the fact that the finite field without 0 is a cyclic group. So because it's a cyclic group, we can take some generator, say G. Right? Then if we want to find the generator of the subgroup, F square root Q star, we just need to raise to the right power, G to the power square root Q plus 1. But for Paley graph, Q is always even. So Q is always an odd prime power. So square root Q plus 1 is always an even number. Okay. So now the generator of this is G to some even power. Right? So the generator is already a square in the larger field. So of course all the elements in the subfield are squares in the large field. So this shows that the subfield in this case forms a clique when Q is a square. So when Q is a square, we already deduced the upper bound, which is square root Q, because we already deduced the clique number, which is square root Q, because we have shown the upper bound, which is square root Q, and we give a lower bound construction at the subfield. Okay. So that means that when Q is a square, we already solved the question of clique number. Right? So now I want to move on to the first half of the talk, which is we consider the case where Q is not a square, because when Q is a square, we already know the clique number is square root Q. And I want to, before I mention the known result and the progress made recently, I just want to mention that in this case, estimating the clique number is known to be a very, very difficult question. And we will see why this is difficult. So first I want to mention some lower bounds. I think Sally gave a talk on this a few months ago, so I won't talk too much about this. So first, so this has some connection with Ramsey number and random graphs. We all know that we have the first Ramsey bound by Aldrich and Sackerich, which says that R is equals 4 to the n. And then we can use this to deduce the lower bound of the clique number of Paley graph. The reason is that Paley graph are short complementary, so that like cliques and independent set are essentially symmetric. So we can just apply the bound for diagonal Ramsey number. So we can get the first non-trivial bound, which is log 4q. And then we can use the fact that Paley graphs are strongly regular to deduce that Paley graphs are actually quasi-random. So using the quasi-randomness and combined with actually off-diagonal Ramsey number bound, we can get a bound which is log 3.008q. And this was actually first proved by Thomason around 40 years ago. So you all know that there are some recent breakthroughs in diagonal Ramsey number. So in particular, we can improve 4 to 3.8. But also in their paper, they have some off-diagonal Ramsey bound, which are significantly better than the Aldrich-Sackerich bound. So if we just combine the idea of Thomason and the recent breakthrough on rounding number, we can get some bound which is like log 2.936Q. Okay. So I think it's well believed that the clique number should be at least log 2Q, or perhaps a little bit larger than that. Because if we assume that Paley graphs are truly random, then if we consider the clique number of a random graph with edge density half, we know we would expect the clique number to be 2 times log 2Q, almost surely. But because it's not truly random, we cannot just use the previously there to deduce something, but we believe that it's more random than quasi-random, so it should be log 2Q, essentially. So again, this was already discussed in Sandy's talk, so I won't talk too much about this. Okay, so this is for the lower bound. What about upper bound? So this is a very dense slide, but this is not the focus of the talk. I just want to mention what's the state of art without going into the technical stuff. So we mentioned about the square root p upper bound. So here p is a prime. So the square root p upper bound was discovered in 60s, I believe. And then there was no improvement for 50 years. And then the first improvement was made by Beckhoff, Mataroshi, and Ruja in 2013, where they just improved the bound by 1. Okay, and then I guess 5 years ago there was a breakthrough by Hansen and Pachidis, where they improved the bound by a multiplicative factor. So they improved that to square root p over 2 essentially. So more precisely, they show that if A is a clique, then A squared minus A is m of p minus 1 over 2. So if you solve this quadratic equation, you can get this square root p over 2 plus 1 bound. Okay, and I want to mention that there was a very recent breakthrough by Kamini, where he showed that if p is at least 17, then you can improve this upper bound by improve this upper bound by 1. Right. So if you take the square root, actually it only improve the Hansen-Pachidis bound by epsilon, where epsilon goes to 0 as we got into. Okay, so yeah, I mean this kind of indicates the difficulty of improving the upper bound. And I want to just briefly mention why this company's work is highly non-trivial. So the reason is that to improve this bound by 1, you need to first solve a conjecture by Levinson, namely that there is no A, there's no subset A of Fp such that A minus A is all the squares. So I just want to quickly show why to improve this bound by 1, you have to solve this conjecture first. So the reason is actually quite simple. So that's assume that the left sum conjecture is false. Okay, so that means we can find some A such that A minus A is everything in Fp, all the squares in Fp. Okay, so we know that the number of squares in Fp is p minus 1 over 2. So this contains p minus 1 over 2 non-zero squares, and of course also 0. And for A minus A, we know that just collection of pairwise difference. So in particular, 0 appears exactly 8 times. Right? So the non-zero element in this is at most A squared minus A. So this means we have to make sure that A squared minus A is at least p minus 1 over 2. Right, so the left sum, if the left sum conjecture is false, then we can find some clique in a Paley graph such that a squared minus a is at least p minus 1 over 2. Okay, but on the other hand, Hansen attributes show that it's at most p minus 1 over 2. So this shows that we must have this being exactly p minus 1 over 2. Okay, you can see now that to improve this bound by 1, we have to solve the left sum conjecture. Okay, otherwise you cannot show it's at most p minus 1 over 2. Okay, so I just want to mention that together with Sangyang and Semi, we provided a simpler proof of this result. So all of these results are based on some method called step-notch methods. Some method initially using arithmetic geometry, but here we are just using a kind of a toy version, which is kind of elementary. So I won't talk too much about this method, but I want to talk about what's our conjecture. Sorry, not our conjecture, what's the wide belief conjecture. So wide belief conjecture is that the number should be very, very small, should be log p to some power. But you know that the state of art is roughly square root p over 2. And even improving this seems to be extremely difficult, by 1. So if you can show this is p minus 5 over 2, I would like to see that. Okay. So next I want to mention some connection between this clique problem and the finite geometry. So actually, I already, you can already kind of see there's some geometry going on here, because you can view this as kind of taking the slope of certain line, right? Yeah, so this is actually precisely why this problem is related to finite geometry. So I want to just talk about the slopes in finite geometry. So it turned out that people prefer to call that directions. So we have a plane. So in our case, the plane is our finite field fq, so it's just fq times fq. And we have some points at u. And we can just use this kind of coordinate ai, bi. Then the set of direction is precisely the set of slopes. You just consider this kind of ratio, bj minus bi divided by aj minus ai. So this is a subset of fq union with infinity, because you could divide by 0, so that's the vertical direction. So you can also think about this as the projective line if you prefer. For direction set, this is a classical object in finite geometry, and there are many results. So I just want to mention one of the kind of the fundamental result. So it says that if we have n, which is at most p point in AG2P, so p is a prime, then the number of directions is at least n plus 0 over 2, unless we have an obvious obstruction, namely all the points are collinear. Because if all the points are collinear, of course there is only one direction. But this result says that assume that they are not all collinear, then the number of directions is at least the size of the point divided by 2. This was resolved by Remy in the 70s when n is equal to p, and this was further extended by Cerny in 91 for all n less than equal to p. Okay, so I want to mention how can we use this direction idea to get improved upper bound on the clique number of Paley graph. So this was resolved by my PhD supervisor, Joseph Sermosh, and his two students, Di Benedetto and Ethan White. So this result by Cerny says that if we have a point set which are not all collinear, then the number of directions at least the size of point set divided by 2. So what they prove is that if we know that our point set is just a Cartesian product, then the number of direction is roughly the size of the Cartesian product. So this improves this bound by 2, right? Because this is essentially saying that if we have a Cartesian product, then the number of direction determined by this point set is at least the number of points in this point set. So let's improve this bound by 2. Okay. So let's see why is this related to clique number. So the reason is actually quite similar, and it has appeared in the proof of the trivial upper bound. So that's A be a clique, and we consider our point set to be this Cartesian product. So the nice thing about this Cartesian product is that the direction set is precisely a minus a divided by a minus a, right? And we know that because a minus a is a subset of squares, a minus a is a subset of squares, so this ratio set is also a subset of squares. Of course, we also need to include 0 and infinity. So that means that this ratio set has size at most p minus 1 over 2, which is the set of non-zero squares, plus 0 and infinity, so plus 2. Right? So this means the number of directions is at most this, but the result by them also gives the lower bound on the number of directions. So you can just compare this lower bound and the upper bound. So you can cancel this plus 2. Right? So you can precisely count the Hansen-Prejudice bound. Okay, so this is a kind of an easier proof compared to Hansen-Prejudice, but you have to show this first. So the proof of this is not easy. It also kind of uses Stafford-Morse method. Okay, so now I want to talk about some extension of this. So you might wonder why here we only work on FP, or P is a prime. Does it extend to general finite field? So the reason is no. The answer is no, because we can consider, for example, our field to be have size q, has size p squared. In this case, if you just take A and B to be the subfield of size p, you can show that the direction determined by this point set is precisely p plus 1, because actually we are lying in the subfield, right? So all the directions are in the subfield. So even if we are working in the larger field, we do not see anything outside of the base field. So this shows that actually in this case, the conjecture, this result is false, because the size of this point set is p squared, but the number of direction is just p plus 1. But their result shows that the number of directions should be at least as large as the point set minus some small things. So this result failed to extend to general finite field. Okay, and this should be kind of should be consistent with the result we discussed earlier, because if this result actually extends to all the finite field, then you will show that for all the prime power q, which is 114, you have this upper bound on the clique number. But previously we have discussed that when q is a square, the clique number is precisely square root q. So this cannot be true be all finite field. Okay, so one result I proved is that I try to think about the general finite field case, because I want to show some result on clique number of this kind of Paley graph defined over a general finite field, not just FP. So the idea is that if we can prove a generalization of this, then we can just apply the same idea to get a bound on the clique number. So to do that, I need to overcome the subfield obstruction I mentioned earlier. And I prove something like this. So this is very complicated. But essentially, what happens is that as long as this subset is large, this point set is large, and we have some technical assumption on the size of this set A and B, then we can still show the number of directions is roughly as large as the point set. So I don't want to go into the details of this because it's quite technical, but I want to mention that this has an application which is if we have a kind of a Kelly graph, then we can give a bound like this. So the upper bound is given by square root of the ratio set S over S has square root Q over P, where Q is a power of the prime P. So P is the characteristic of the field. So you can see that this result recovers the result by Hansen-Pagidis immediately, because in that case S is a subgroup, so S over S is just S itself. So in that case it's S has size roughly P over 2, so this is just square root P over 2, and this is 1, because Q is equal to P. And it also extends the Hansen-Pagidis bound to all the Paley graph of non-square order, because again, S is a subgroup, so you get something like 1 plus beta over 1 times square Q over 2. And I think more importantly, this result is actually asymptotically sharp for infinite family of generalized Paley graphs. So this shows that the Hansen-Pagidis bound is in certain sense best possible, because the shape of this bound is kind of like square root of this S over S. Right? So this means that if we want to improve Hansen-Pagidis bound, we must use the fact that our set S is a set of squares, and also we are working in a prime field. So if the proof doesn't use these two, then it cannot improve the Hansen-Pagidis bound. So this shows that the Hansen-Pagidis method and the signalization have certain limitations, because if we consider a larger family of graphs where this kind of technique works, the bound is actually best possible. You cannot improve that. So that means that if you want to improve the clique number for Paley graph, you have to come up with something completely different. Okay, so the second part of the talk is about square order, because in this case we already know the clique number is precisely square root Q, but maybe we want to say something more. We want to characterize all the maximum cliques, and this is precisely what we will do. So I mentioned earlier that in this case we would kind of expect that all the maximum clique have to come from the subfield because of the sum product phenomenon. And this is actually precisely the conjecture by Lint and MacWilliams in 1978. So their original motivation is coming from Collins theory, but I think this conjecture is of independent interest in the context of Paley graphs. So their conjecture is precisely about the structure of maximum cliques in Paley graph of square order. So more precisely, if we have a subset A of this FQ squared, such that 0 and 1 is in A, so there's some normalization, and the size of A is Q, so it's the maximum clique, right? Then A has to be the subfield. So that's precisely a conjecture, and this was first proved by Vertices in 1984, and later Blum and Fisher provided a different proof. A few years ago, my collaborator Shaman Asghari and me provided a new proof, and earlier this year provided another new proof, which extended to a more general setting that I will talk about in the next few slides. This result is also sometimes known as the Aldish-Prado theorem in Paley graphs, because if you think about this subfield, this is kind of like the obvious clique. Right? So the Aldish-Prado theorem basically, essentially is about certain kind of intersecting family, and we want to say that all the maximum intersecting family should be those obvious ones, like stars. So in this case, you can view this kind of subfield and those kind of function state as the obvious cliques. So I can, so actually we can formulate this in terms of intersecting family, but I don't think I have time to talk about that. But sometimes this is known as the Aldrich Cradle theorem of Paley graphs. Okay, and Broca's proof is based on an ingenious polynomial method. So there are also many recent breakthroughs using polynomial method. And you may ask what's special about squares, right? So can it be extended to more general Paley graphs? So one realization was studied by Clique, where he studied the same for D Paley graph. But you need to have one more assumption. So I'm sorry here, the notation is probably not consistent. But the idea is that we need to have D divides Q plus 1. So here it should be Q. So D divides Q plus 1, and we consider the connection set to be all the D's powers. Then his result says that in this graph, all the maximum clique have to come from the subfield. This is precisely a generalization of broadcast result. The broadcast result is for just for D equal to 2. And this assumption D divides Q plus 1 actually guarantees that the subfield forms a clique. Okay. So I mentioned earlier that perhaps we want to consider more general family of graphs other than just the connection set being a subgroup. So the natural question is, what if we just replace this connection set S, which is a subgroup, by something which has nice multiplicative property, namely that the doubling constant is small. So that's something that I'm interested in, and also there are some conjecture by others which is about this. So the first thing I try is to read their proof, but I quickly realized that their proof cannot be extended to the general setting, because their proof is based on a polynomial method, and the polynomial they constructed is quite rigid in the sense that it highly relies on the fact that the connection set is a subgroup. So if the connection set is not a subgroup, their polynomial cannot be modified to work. So that means we need some different method to handle this. So this is the result I proved. So you can see that this has appeared in the previous slide. I mean, you might wonder why this is relevant, but it's kind of it's from the proof. So I cannot say why this is relevant, but it comes from the proof. So it says that if the connection set S satisfies this, so S inverse is the most roughly Q square over 2. Then if we consider this Paley graph, then all the maximum cliques have to come from the subfield of Q. And I just want to remind you that this kind of condition is not kind of unnatural, because suppose we have a set S with small doubling constant, say K is the doubling constant. Then again, I can apply Punnett-Ahuja to say that this S inverse has size at most K to the power 6 times S. So if K is kind of small, for example, K is at most 2, and S is not too large, then this condition is actually quite easy to be satisfied. Right? And also in the special case where S is a subgroup, you know that there is no expansion here, so we just need the size of S to be less than this. So this result immediately recovers the result by Broca's and Clique, and actually a few other results. Okay, so maybe in the remaining time, let me just quickly sketch the proof and then end the talk. Okay, so the idea of the proof is that step 1 of the proof is that
can you use different color?
a different color. which color would work that?
Any other color?
This red?
Whatever.
Okay. Let A be a maximum clique. And that's shown that it contains 0 and 1. So step 1 of this proof is that I want to show something weaker. So our goal is to show S is a subfield, right? So first I want to show something weaker. I want to show A is a subspace. So by subspace I mean it's a vector space over Fp. Where P is the characteristic of the field. So I want to first show A has an algebraic structure. Okay, and step 2. I want to show that 1 over A is also a subspace. So here by 1 over A, I mean consider all the reciprocal of non-zero element. And then I join with 0 because we assume that 0 is A. Right? So I want to show 1 over A is also a subspace. And then step 3 is that I apply some lemma, which is actually not too difficult to prove. So this lemma says that if A is a subset of FQ squared with size precisely Q, and 0, 1 is in A, then and also A and A inverse, 1 over A, are both subspaces, then I can show that A has to be the subfield. So I want to kind of reverse, I want to first explain step 3. So step 3 is actually not not too difficult to understand. A is a subspace, means it has nice additive structure, right? And 1 over A is also a subspace, so that means 1 over A also has nice additive structure. But here we do the kind of division. So it means A has to have very, very strong additive and multiplicative property. So it's kind of easy to show that A has to be the subfield. There's no other choices. Okay, and for the second step, I want to just illustrate this by a particular example. So let's just consider the case where our graph is the Paley graph. So I want to show that if A is a maximum clique, such that 0 and 1 is in A, then 1 over A is actually also a maximum clique. I guess I just need to show 1 over A is a clique because 1 over A has size Q. Right? So I want to show 1 over A is a clique, and the proof of this is actually quite simple. We just need to check this by definition. So take X and Y in A. Right? So to show 1 over A is a clique, I just need to show that 1 over X minus 1 over Y is a square, right? So let's just kind of do some manipulation. So it's X, Y, Y minus X. Okay. So something to notice is that 0 is in A. Right? 0 is in A means that if X and Y is in A, they must be square. Right? So this means that X, Y is already a square, because both X and Y have to be squares. And we know that Y minus X is a square by definition, because A is a clique. So square over square is a square. Okay. So this shows that 108 is a clique. So essentially, step 2 reduced to step 1. Okay, and to show step 1, I used a result on directions. So if you recall from this result on directions, so it says that a point set either determine, let's just say we have a point set of size p. It says that either we determine p pass 0 with 2 directions, or this point set has a strong geometric property, namely it forms a line, right? So there's a generalization of this result by Blockhouse, Blauer, and Cerny, and Bohr, and maybe a few others, which extend this result to a general finite field. So the statement is that if we have q point in AG2Q, q is a prime power, then either we have at least precisely q pass 0 with 2 directions, or they have some geometric property, namely lies in a subspace. So if we just apply this generalization, we can prove this, because if you go back to this, if we consider the same point set, the number of directions is almost p plus 0 with 2. So this is very, very close to this, right? So this shows that this has to be a subspace. So of course, in the general case, the proof is more complicated, but this essentially demonstrates the key idea. Yeah, so I think that's all I want to talk about. Thank you very much for your attention.
Thank you. Any questions?
Why don't you apply the Hofmann's ratio bound for bounding the Clique number of the generalized Paley graph? Because this Paley graph is some kind of a Paley graph, so you can calculate its the spectrums, the eigenvalues by summing of by using the calculating the character sums. So maybe you can apply the Hofmann's ratio bound.
Yeah. That's a very good question. So actually, if you just apply the Hofmann bound, you get precisely square root 2. And improving that seems very difficult. And also, Hofmann bound actually has the second part, which says that if the equality holds, then certain kind of condition have to be met, right? So that's actually one possible direction to prove to characterize the maximum clique in the case of square. But I try very hard, but it seems it doesn't work.
So at first time you mentioned about some generalized Paley graphs. Can you generalize every result for the generalized Paley graph?
Yeah, of course, because let's look at one my result. Yeah, so for this one, right? For this one, like, if S is a subgroup, this is just a size S. And for this result, I mean, if S is a subgroup, then it has no extension. So as long as the subgroup has size at most q squared over 2, which holds for all non-trivial subgroup, you can have this result. So my result extend all the result on Paley graph, generalized Paley graph.
So in a sense, so when you prove the omega is small, that means the complement has large chromatic number, because when you take a complement of the graph, then you don't have a small independent set, so the chromatic number should be big. And so I wonder whether the lower bound on the chromatic number of the complement is known, or whether it's a type.
So in the case of Paley graph, it's short complementary, so the graph is complement isomorphic. So starting the chromatic number of complement is the same as starting the chromatic number of itself. So I guess the best known bound of chromatic number actually comes from clique number. So I guess we have some relation between clique number and the chromatic number. I guess their product has to be less than have to be greater than the size of the graph. You can
Yeah.
correct? Yeah. So using the upper bound the clique number, you can get some lower bound number.
So do people know whether it's tight or?
I think it's believed to be far from tight because of the bound on the clique number we know is far from tight.
Maybe I missed something, but maybe you used the sum product estimation in your group.
I didn't use any of the sum product estimate, but the sum product
But one of your motivation is the sum product.
yeah, the sum product phenomenon kind of tell us what's the expectation of the clique number. So in the case that we do not have a kind of obvious construction, we would believe that the clique number has to be small. And in the case of Paley graph or square order, this conjecture is kind of predict that large clique must be subfield. Yeah, so I didn't use any of sum product estimate in my proof, but this is kind of the underlying kind of the bigger picture of this kind of question. So all of these questions can be realized as special questions in the sum product phenomenon. But for the sum product phenomenon, we actually don't really know this. So that's why we cannot apply this kind of result. But it fits into this big picture.
Any other questions? So if not, let's thank the speaker.